Today is Thursday, the 5th of March. Lecture 16, we are on the downhill part of this semester, people. On our way to completion. All right. Well, 3. If I count 4. So, all right. Hello out there in TV land if you are watching live or if you are watching on record. Record, that was weird. All right. So here we go. We're going to talk about linear momentum today. So this is, let's just kind of reactivate where we're at. So last class we did energy grade lines and hydraulic grade lines, which was like a visualization of the energy equation. And you had some examples to work on yourselves, and I just posted the solutions for those in the Lecture 15 folder. And you've got a homework problem or two that involve HGLs and EGLs. The core, what I think of as the core of fluid mechanics, is being able to manage conservation of mass, conservation of energy, and conservation of momentum. Okay? We've done conservation of mass, we've done conservation of energy. So sort of the last new topic for us is conservation of momentum. And so we're going to spend maybe 2 to 2.5 lectures on this idea of conservation of momentum. And so much like in hydrostatics, we learned about hydrostatics, and then we saw how not moving fluids interact with the world around them, how fluids at rest can exert forces, right? And so that was like forces on a planar surface, forces on a curved surface. Momentum is where moving fluid starts to be able to exert forces on the world around it. So how does a fluid in motion exert forces? And so we'll start, we'll do a little bit of sort of background on linear momentum. We'll see some examples of momentum so we get our head around what momentum is. And then we'll do some examples. I think this is more easily learned through examples than theory. So we'll have covered mass, energy, and momentum, which makes it seem like we're going to be done when spring break gets here. So after spring break, we'll just start tweaking everything that we've done. So we'll loop back, and in particular, we're going to loop back to that head loss term, and we're going to talk about how you can know where energy goes. And then after spring break, we'll also look at what are called external flows. So we're often right now focused on flow within something, within a channel, within a pipe. We're going to switch to what happens when there's a big flowing fluid and the thing moves through it. Instead of fluid through a pipe, what if you move an airplane through a fluid or a submarine through a fluid? So that's kind of where we're heading. I better mute that before we blast us all again. All right, so learning objectives for today, being able to apply conservation of momentum, and then being able to invoke momentum along with energy and mass to solve even more complicated problems. Just like once in a while, like last class, I made a point of showing that we were actually invoking conservation of mass as part of the energy problem that we did on the pipeline. We're now going to be able to invoke energy and mass and momentum and hydrostatics if we need to. And so your toolkit of equations and things that you can work with is growing. All right. So momentum, a couple of kind of physics demonstrations. Right, so in this one, the fast-moving vehicle is transferring momentum to the one that moves slower. Right? So the slow-moving one that comes from the right, when these things come in contact, this thing actually, not only does it reverse its direction, but some of the momentum we had here transfers here. That slow one is accelerating to just about the speed the fast one was moving. So that's a really 1D look at momentum. Momentum can also happen in multiple directions, right? This is how billiards works. This is how air hockey tables work. That a portion, even though this first disc is sort of sliding in one dimension, right along what we think of as like the x-axis, it can interact here, and components of that momentum can get generated. So motion that was primarily directed in one direction can generate motion in other directions when it interacts with these objects. Momentum. That's why it's easier to hit a fastball out of the park than a changeup, because that baseball has momentum. A changeup is a very slow pitch. So a fastball is when we throw the ball as fast as we can. A changeup is when you look like you're about to throw it as fast as you can, and you actually throw it extremely slow. And it leaves the batter looking like a fool because they swing, and then the ball comes by. So it's easier to hit that fastball out of the park because it has more momentum to begin with. And so you are changing the direction of it, but you're able to do that. Momentum is also the reason that if you hit on the wrong part of the baseball bat, you can snap it. That moving baseball exerts enough force that it can actually snap that moving bat. Finally, in what might be the most practical example, the good folks of Jackass.
I'm Dave England, and this is the Fire Hose Rodeo.
The reason that this looks like fun, the reason that this hose can actually move a human up in the air, is also momentum. Right? That moving fluid coming through the fire hose has enough momentum with it, has enough energy with it, is able to exert forces in such a way that it can actually lift that person off the ground and make him swing around like a jackass. Okay. Momentum, force. Force is getting transferred, things changing direction, generating forces when we interact with other objects.